Okay, so this video talks about the chapter 5. So in chapter 4, we learned regression with a single regressor, and chapter 5 talks about hypothesis test and confidence interval for the regression with one single regressor. Okay, so I want to pause here in the second page. So you're only required to learn the first 4 points. Okay, why is the first point separated from the rest? Okay, so you're only required to learn the first 4. The 5th and the 6th are not required. Okay, but it is sometimes unavoidable that you might see these 2 words. So I'm going to explain what they are, but remember that these 2 are not required. So sometimes if you see it, it doesn't really prevent you to get to know how to solve the question because so far we don't require this part. Okay, but just for curiosity, I'm going to explain what they are. Okay. And the 6th part, efficacy of OLS and the student t-distribution. This part is more of a advanced econometrics knowledge. So I wouldn't say this is very important. But of course, if you are pursuing a graduate school in the future, then you can take a look at it. Okay. All right. So first, we start with the first section, the standard error of beta 1 hat. Okay. The big review of what we're going to do here is that we care about the slope. Okay. And there's a population slope. There is a sample slope estimator. We want to use the sample slope estimator to tell us something about the population slope. And this estimator, after we satisfy all of the assumptions, is normally distributed. So this estimator has a standard error. Once we know the standard error of this estimator, then we can have a, let's say, imagined distribution for the estimator. Once the estimator has a distribution, then we can do hypothesis testing and confidence interval. Okay. So first we need to start with the standard error for the estimator. Okay. So the object of interest is beta 1. Remember, beta 1 is the population slope. Okay. The slope in the population. Okay. In the broad population, all the students out there, what's the relation between student-teacher ratio and test scores? Okay, and then we end up having an estimator that is calculated, okay, that we can get it from the sample we get, okay. In this specific case, we have about 400 school districts, okay, but this 400 school district is only a sample. So we have beta 1 hat as our estimator. And we know that it has a sampling distribution because these 3 assumptions has to be satisfied. Okay. So again, we care about beta 1, but we only have beta 1 hat as the estimator. Okay. So we want to know estimator beta 1 hat's distribution. How do we know its distribution? We know it because we can satisfy 3 assumptions. In this class, we're going to assume that these 3 assumptions are all satisfied. But of course, if you go to more advanced econometrics class, sometimes it's not satisfied. Then you have to find out other ways to go around with it. Okay. After we satisfy these 3 assumptions, which all of you should remember what they are, we know that beta 1 hat is normally distributed. Okay, So this is the distribution of beta 1 hat. Its mean is exactly beta 1, which is the population slope, and its variance is this part. Okay, it's called sigma v squared divided by n times sigma s square. Okay, so you don't need to remember this equation. Okay, you just need to know that beta 1 hat, after we satisfy the three assumptions, it is normally distributed with its mean at exactly the population slope. Okay, so now the objective is to test a hypothesis, like whether the slope is zero or not. Okay, it's very typical for us to test whether the slope is zero or not, but in some cases, it could be whether the slope is -2 or not, or is the slope larger or smaller than -2. So using the data to reach a tentative conclusion whether the null hypothesis is correct or incorrect, or whether the null hypothesis will be rejected or not rejected, the general setup looks like this, okay? For a two-sided test, okay, we have H0, beta 1 equals to beta 1, 0. Okay, so here, this one is the population slope. And at the right-hand side, beta 1, 0 is the hypothesis value. Okay, sometimes this value is 0. And if it's a two-sided test, then H1 should be unequal. Okay, you need to have an unequal sign in H1. While if it's a one-sided test, the null hypothesis remains the same, but H1 becomes smaller or larger. Okay, could be smaller, could be larger. Okay, all right. The general approach is we need to construct a t-statistics, okay? The t-statistics equation is the same in our previous chapter 3, okay? T equals to estimator minus hypothesized value divided by the standard error of the estimator. For testing the mean of y, this one you should be familiar with it. T equals to y bar minus hypothesis value mu y0 divide by the standard error. Okay, the standard error here could be sy divided by sn. I think there should be a typo here. It should be lowercase s. Okay, this one's not so accurate. Okay, you can have lowercase s divided by, oops, no, you can have lowercase s divided by square root of n, or in some cases, if you know the population sigma, then it would be sigma divided by square root of n. Okay, so these two are the standard error when we are testing our y bar. Okay, for testing beta 1, okay, this equation you need to remember, or you need to put it in your notebook or something, that T equals to first estimator, in this case is beta 1 hat, minus hypothesis value, in this case it is beta 1, 0, divide by standard error beta 1 hat. Okay, so here you don't need to remember the equation of standard error, because standard error is usually provided for you in a question. So we'll go through a lot of exercise here. Okay, don't worry about it. And standard error of beta 1 hat is the square root of an estimator of the variance of the sampling distribution of beta 1 hat. Okay, so yes, y bar has a distribution and has a standard error. So beta 1 hat also has a distribution and has a standard error for itself. Okay. All right, so this page is quite important. Make sure you understand everything here. Okay. So next, formula for standard error beta 1 hat. Okay, this page is less important. You don't need to really understand what's going on here. But if you're curious, I'm going to explain to you. So this is how we calculated standard error of beta 1 hat. We try to get the variance of beta 1 hat first by calculating the variance of xi minus mu x times ui. Okay. This one is mu x. Okay. What is mu x? The average of x. Okay. This one is ui, which is the error term. Okay. Again, this page is not required. Okay. Don't freak out. Okay. Or don't take notes. This page is not really required. What you need to take a look at here is just maybe this part. Okay, let me see. Is there a final version of this? No. Okay, probably what you'll need to look at is probably this part. Okay, so sigma hat of beta 1 hat square is standard error of beta 1 hat square. Okay. So standard errors square equals to this thing. Okay. And you can see that there are so many n here, which makes you so confused. But basically, you can have an idea that this thing has something to do with the variation of x and also the value of n. Okay. Um, okay, I should skip this part so that you don't get confused. All right. Pay attention. Page 7 is very, very important. You need to make sure you understand everything here. Page 8 is the process of how to get standard error. Okay, page 8 is not required. Okay, don't freak out. Page 9 is an explanation, kind of like it says this is a bit nasty. Okay. I didn't know they can use this kind of language here. Okay, this is a bit nasty, but it is less complicated than it seems. The numerator estimates variance of v. The denominator estimates variance of x squared. So why the degree of freedom adjustment is n minus 2? Because there are two coefficients being estimated. Okay, these part not really required. Okay, so page 9 is also not required. But this thing is very important. Okay, you should remember this. You should be happy to remember this. Standard error of beta 1 hat is computed by regression software, usually. Okay, so in a word, in Y bar, you have to calculate standard error on your own. But in beta 1, great. You don't even need to calculate it. You could just take it from the question. So it sounds like econometrics is even easier to study comparing to statistics, right? It's just simple. It's everything automated by the computer. You just ask the computer to run the regression and the computer tell you the slope, okay, the estimate of the slope and the standard error. Okay, so you then have everything. Then you can calculate confidence interval and t-statistic and all those hypothesis testing thing. Okay. All right, so is regression really easier than statistics? We need to see. All right. Okay. Page 7 is important. 8 and 9, not really. Okay. So summary, to test a two-sided test, okay, we need to construct a t-statistic that equals to beta 1 hat minus the hypothesis value, beta 1 0, divide by the standard error of beta 1 hat. Okay. We will reject a 5% significance level if the absolute value of t is larger than 1.96. Okay, this one should be familiar with all that all of you should be familiar with. In terms of p-value, okay, remember that I remember that I think you should use the phi minus absolute value of t. Okay, 2 times. Okay, in the two-sided test, right? So in the two-sided test, p is 2 times phi minus absolute value of t. Okay, if you're comfortable with this equation, it's also fine. Then if it's smaller than 5%, then you reject, okay? Or the test is significant at 5% level. Okay, so this residual relies on a large n approximation that beta 1 hat is normally distributed. Typically, what is large n? N is 50, okay? So you can think of it as if you run a regression of 50 states, let's say GDP on something, whatever you think of, okay, then do we have a normal distribution of beta 1 hat? And the answer is yes, because we already have 50 states, okay? Or you can really argue that is 50 necessarily good enough? Is 49 necessarily bad enough? But most of the cases that we encounter, especially in today, there are more and more big data out there in the world. We don't really care about this anymore. Okay. But in a clinical trial, let's say you design an experiment and every observation costs you money, right? Because every observation you have to assign people to do it, you have to hire volunteers, you have to pay volunteers, you have to buy equipment or something. Then at that time, you have to have other tools to decide what's the minimum amount of observations you need in your specific experiments. Okay, so n equals to 50 is large enough, and this is usually easily met. Okay. All right, so this part is so familiar to you. I don't have any doubt that you can't do it. Okay. Once we do t-statistics, oh, there's an example here. Okay, so estimated regression line is test score equals to 698.9 minus 2.28 times STR. Okay, so which one is beta hat, beta 0 hat? The 698.9. Which one's beta 1 hat? Minus 2.28. Okay. And the regression software tells you the standard error. Okay, that feels nice. So you put the minus 2.28 here, and you're testing a null hypothesis that is beta 1 equals to 0. So you put 0 here. And then you divide it by standard error, which the software gave you, and you get a t-statistic that is minus 4. Okay. And obviously, this is significant. Okay. Alternatively, you can also compute the p-value, which should also be a very familiar exercise with you. That is also why in this semester I spent quite a longer time on chapter 3, so that if you're familiar with how to do a test for Y bar, then here you just feel that you are just enjoying it because you don't need to have a very steep learning curve. Okay. This is how you do it. Usually you use an Excel function to do it. Okay. Oh, usually you use an Excel function. Okay. P-value, because this is a two-sided test, right? So P equals to 2 times this minus 4.38. So it is 2. Okay, don't remember to times 2 minus 4.38. All right, so put this into the norm dot s dot dist. Okay, and then times 2. And this is the p-value you get. It's so small, so you reject the null hypothesis. Okay, simple, easy, intuitive, and nice. Okay. All right. After hypothesis testing, you can also do confidence intervals for beta 1. Recall that a 95% confidence is equivalently the range that you cannot be rejected at the 5% confidence significance level. Okay, they are two sides of one mirror. So, okay, forget about these words. This is the equation that by now you should be very familiar with, but we are just changing the mu here. Oops. We're just changing here. We change the mu y to beta 1, and then we change y bar to beta 1 hat, right? And how about standard error? Okay. In the y bar case, we need to calculate the standard error by ourselves, but it's not really a big deal. Okay. This one can also be s divided by whoops, s divided by square root of lowercase n. Okay, depends on whether you know sigma or you know s. Okay. All right. And of course, if it's a 99% confidence interval, then it should be 2.28. If it's 2.58, I believe. And if it's a 90% confidence interval, then it should be 1.465. I believe that Pearson also take 1.64. Okay, so just try. All right. See which one it takes. Okay. I don't even know what to explain. Things are very clear. Okay. Oops. Okay. So this is the example for the confidence interval. Again, put into all the numbers. Okay, I don't see anything that you cannot understand, to be honest. Beta 1 hat is minus 2.28. Okay, you find this in the regression function. And then this is the standard error. Okay, put the standard error here. Then you calculate and you get minus 3.3 to minus 1.20. Okay, so if I ask if you can you test H0 that beta 1 equals to minus 1? Yes, because minus 1 is not inside this range, right? If minus 1 is not inside this range, then I can reject beta 1 equals to minus 1 at 5% level. Okay. Can I test beta 1 equals to, okay, two-sided test, okay. Can I test beta 1 equals to minus 4? Yes, because minus 4 is also not inside this range. So we can reject this at 5% level. Okay. Can I test H0 beta 1 equals to -2. Okay. This one I cannot reject, right? Because -2 is inside this 95% confidence interval. If it's inside that, that means I cannot reject my null hypothesis. My null hypothesis might be true. Okay. It might be true, it might not be true, but I just can't say um, I just can't say that I'm 95% confident that it's not true. Okay. All right. Or just think of, okay, I cannot say it's not true at this confidence level or at this significance level. Okay. All right. Next, a concise and conventional way to report regression. Um, Usually in the future, you will see that every regression you will see the slope in the coefficient, and at the same time you will see below them there is a standard error. Okay, and at the same time what we also see is an R square. Okay, SCR doesn't show up that frequently, but sometimes it's here, sometimes it's not. Okay, so here we have beta 0 hat, we have beta 1 hat, and these two are the standard errors for beta 0 hat and beta 1 hat. We usually just put it under there. Is standard error always positive? Yes, because standard error is kind of like standard deviation. It's estimate how spread out your distribution is. So it is always positive. Okay. So this expression gives a lot of information, and every time you see this, you should know what each number means. Okay, you should know that you should be able to quickly tell me which one is beta 1 hat, which one is beta 1 hat's standard error, which one is beta 0 hat, which one is the standard error for beta 0, and you should quickly tell me which one is R square. Okay, and what does R square mean? Okay, so what does R square mean? It means that student-teacher ratio only explains the variation of test score by 5%. Okay, or student-teacher ratio explains 5% of the test scores variation among the school districts. Okay, so where are the rest of the 95%? Okay, all the other things in the error. Okay, what are the other things in the error? We can think of their language ability in the school communities. We can think of the average income level of the school communities or school districts, or we can think of school fundings or school technology level and or other policy. Okay. All right. Okay, so page 15, very important. You should know what each part means. Okay. SCR, not so important, but you at least you need to know what it is. Okay. It is the standard error of the regression. Okay. The standard error of the regression. Okay. Not not for the coefficient, for the regression. And you should know that SCR has the same unit as Y, which is a score. Okay, and that's it. Okay, it doesn't really mean anything. Okay, so we always care about R square much more than SER. All right, next. This is the data output. I'm gonna skip here because in the future I'm gonna teach you Python. So we learn how to read Python or Excel regression output. Okay. All right, summary of statistic inference. Estimation, we estimate, if we only have one regressor, then we estimate beta 0 hat, which is the intercept. And we also estimate beta 1 hat, which is the slope. Okay. Beta 0 hat and beta 1 hat are both estimators and both have distributions. In our setting, because we assume three assumptions hold, then we have these two estimators, this nicely approximately normal sampling distribution in large samples. So beta 0 and beta 1 are random variables and they have a distribution. This distribution is imagined over repeated sampling. Okay. But in real case, you only sample one time. Okay. You can use this nice normal distribution to do testing and confidence interval. If you do testing, then you can calculate t-statistic using this formula, which you should remember, and to get p-value, which you should already know how to do it. And you can use this formula to calculate confidence interval. It doesn't necessarily is only 95% and 5%. Sometimes on Pearson, you are asked to get 90%, 99. Okay. So it depends on the question. Um, so here I'm gonna introduce you regression when X is binary variable. All right. So first thing is this binary variable. It will show up in one of your multiple choice questions. So what is binary variable? Binary variable is also called dummy variable. It can only take two value, which is 1 and 0. Okay. It can be win and lose. It can be small class and large class. It can be female, male. Okay. Well, but right now you can have more than two genders. Okay. It can be treated and not treated. Okay, if it's in a clinical trial setting. So binary regressors are sometimes called dummy variables. So far, beta 1 has been called the slope, but that doesn't actually make sense if X is binary. So how do we interpret regression with a binary regressor? So first, you should know why it doesn't make sense. Okay, so here is X, here is Y. Okay, imagine this is 0, this is 1. Okay, and this is still test scores. Okay, so we are using this as our example. So imagine you have, let's say, 5 schools. Um, 2 of them are small class, 3 of them are large class. Okay, and now if you want to draw a line, okay, if you want to draw a line, how do you draw it? You probably draw it this way, right? Suppose we have 5 school districts. Okay. Uh-oh. Nope. Uh, suppose X equals to 1 is small class size, then we should have small class that small class should have better grades. Okay. Small class have better grades. And then large class. In the large class, X equal to 0, right? When X equals to 1, it's small class. So I assume they have better grades. Okay, so if we draw a line, then it looks like this. So in this case, a slope doesn't make sense because the slope doesn't mean that, oh, if X increased by 1 unit, how much test score increase? Because X now is only has 2 values. You cannot say X increased by 1 unit anymore. You can only say comparing 2 groups. Okay, so that's how we interpret a regression when X is binary. Okay, we're only talking about X variable. We're not talking about Y yet. Okay, we will talk about Y. Okay, not in this class. Probably in your graduate school, or in your other class, in econometrics. Okay. So here is how to proceed. Okay, so here is how to proceed. We're trying to interpret a regression with a binary regressor that y can be anything, but x variable is a dummy variable, or x variable is a binary variable. So let's see what it really looks like. Okay, if x is 0, then I put a 0 into this equation. Okay, let me change the color. So if x is 0, then, whoops. If s is 0, then I put a 0 here. Okay, what happens is that if this term is 0, then this term is canceled, right? Because anything times 0 equals to 0. Then what do we have? We have beta 0 left, and we have ui left. Okay. In this case, if I calculate the mean, it will equals to expectation of beta 0 plus expectation of u. Okay, this part is not really required, but I'm just going to show you what it looks like. And expectation of u is 0. Okay, because expectation of ui conditional on x is 0. So it doesn't matter. And we will end up getting this. Okay. While if we have x equals to 1, okay, then anything times 1 equals to 1. So this is x equals to 1 times beta 1, right? Then we have beta 1 here. We still have beta 0, and we still have ui. In this case, if I need to calculate the expectation of y, I have beta 0 plus beta 1 plus 0, because the last term is 0. Okay, they're the same. Oh, and these two terms are the same too. So what I get is the mean of yi equals to beta 0 plus beta 1. That is expectation of yi conditional on x equals to 1 equals to beta 0 plus beta 1. So what is beta 1? Okay. Beta 1 is here. Okay. While beta 0 is the same. All right. So beta 1 is, okay. Beta 1 is the gap between this part and this part. Okay, what is part 1? Part 1 is this, and part 2 is this term. Wait, wrong direction. Part 1 is when x equal to 0. So part 1 is this. Part 2 is this. Okay, and the difference between them is beta 1. Okay, some people are into math, so they should be very comfortable with this page. But some people like graph, so I'm gonna show you what graph look like. Okay, let's use a new slide. Oh, this look ugly. Oops. Okay. All right. First of all, you have x-axis and y-axis. Okay. And you have x equals to 0 and x equals to 1. Okay. This is 0, this is 1, this is x, and this is y. Okay. This is x, this is 0, this is 1. Okay. And then let's say we have 3. Okay. And here there are 2. So what does beta 0 equals to? Beta 0 equals to expectation of y conditional on x equal to 0. So it means that it's the expectation of y when x equals to 0. Then it is here. It is here. Okay, this one is beta 0. So this one's beta 0. Let's write it here. Because it's the average of these 2 stars. Okay, because we are getting the expectation of y conditional on x equals to 0. So we don't need to care about these 3 stars when x equals to 1. We only care about x equals to 0. And because we are taking expectation, so it is the middle point of these 2 stars. Okay, so this one is beta 0. Where is beta 1? Okay, beta 1 is expectation of, where is beta 0 plus beta 1? Beta 0 plus beta 1 is expectation of y conditional on x equals to 1. All right, what does it mean? It means that when x is 1, its average value is beta 0 plus beta 1. So where is it? It's the middle one. Okay, let's assume that 3 of them are equally spaced. Okay, so let's go all the way here. Okay, this thing as well. And then this mark is beta 0 plus beta 1. Okay, so then now tell me, where is beta 1? Beta 1 will be the gap between these two points. So I'm going to use the color red. It's a little bit big. Let me change its font. Okay, so the gap between here is the beta 1 that we're looking for. Okay. So visually, it looks like this. If we want to draw the line, then it's this point connected by this point. Okay. Theoretically, the y-axis should be on 0. So the y-axis should be here. But I just want to show you where 0 is. So it doesn't really matter. Okay. So here is our intercept, right? The intercept is beta 0. It means that it's the average value of all the schools' test scores when all of them are 0. Okay, they're grouped by 0, so they are large schools. While the slope is the gap between the small school's average score and the large school's average scores. So the small school average scores is beta 0 plus beta 1. All right, so then now you have an idea between beta 0 and beta 1. Beta 0 is the average score of large classes. And then beta 0 plus beta 1 is the average score of small classes, okay, because we know that small classes have higher scores. And how about beta 1? Beta 1 is the gap of these two groups. Average score. Okay. So let's say small school districts, their average score is 650. Large school district, their average score is 640. Then what is beta 1? Beta 1 is 10. Okay, it's 10 scores. It's the difference between two groups. Okay, so it sounds like we're going back into the two sample t-test. Okay, so in some case it is, okay. It looks very, very similar. Whoops. All right, so I would say that this graph is very important, and we'll go through this graph next week as well, when we go through the exercise. Okay, but I recommend you to take notes of it, that beta 0 is the group when x equals to 0. It's average. Beta 0 plus beta 1 is the average for the group that x equals to 1. And the beta 1 is the gap between these two groups. Okay. All right. Next. Okay, this is the last two slides. Okay. So how do we interpret it? Let's say we have a binary variable that is d, that when d equals to 1, str is smaller or equal to 20. Then that means that d equals to 1, it's a small class. When d equals to 2, when d equals to 0, it's large class. And here, beta 1 equals to, is that more precisely, beta 1 equals to 7.4. So what is 7.4? It's the average score difference between the small group and the large group, right? Because small group is 657.4, and the large group, the average score is 650. Okay, so this is really going back into the two sample test. So I'm not gonna explain too much about it because we already know it. Okay, but think of binary regressor as a two sample test. Will help you quickly feel very familiar with this unfamiliar thing. Okay, I feel like this part is the only new thing in this chapter for you to really feel that, oh, this thing is something new. I don't know what it is, or I feel a little bit scared. But thinking that as a two sample test will help you feel much more comfortable with it. So in summary, regression when x is binary, or regression when x is dummy. You have y equals to beta 0 plus beta 1 times xi plus u. Beta 0 is the mean of y when x is 0. Beta 0 plus beta 1 is the mean of y when x equals to 1. And beta 1 is the gap between two groups average. In this case, the standard error of beta 1 hat has the usual interpretation. You can still use the t-statistics and confidence interval constructed as usual, and it's the same with the two sample test. Okay, so lastly, I'm just gonna quickly introduce you what heteroskedasticity and homozygosticity means. Okay, these two super long, weird words can only be seen in Econometrics textbooks. Okay, you probably will never see it in the rest of your life if you don't do anything related to econometrics. So what does it really mean? It means that if the variance of the u, which is the error, conditional on x, okay, is constant across different x values, then u is homozygosticity. If it's not constant, then it is heteroskedasticity. Okay, words is usually very confusing. So let's take a look at, okay, also skip the math. Let's just look at a graph. So the distribution of y is this, but you can think of it as the u is also this shape. Okay, so the variance of this shape, okay, you can see 3 distribution here. If 3 distribution here is equally spread out, then it is homozygosticity. If it's not, then it's heteroskedasticity. Okay. It doesn't affect the 3 assumptions that we already talked about. Remember, the 3 assumptions we already talked about gave us an unbiased estimator that is normally distributed. So whether the variance is had homoskedasticity or heteroskedasticity doesn't affect that one. Okay, we still have unbiased estimator. We still satisfy 3 assumptions in order to have a normal distributed estimator to do all of our tests and confidence interval. But what does it actually affect? Okay, skip, skip, skip. Is affect variance of beta 1 hat. Okay. So if it affects variance, then it affects standard error. So what's the problem here? Um okay, too much word, don't read it. Okay. After page 21, just forget about it. The only thing you need to know is that heteroskedasticity and homozygosticity, it only matters because the standard error would change, but we do not discuss it in this class. Okay. All right. I look forward to share with you how to cope with the problem sets of this chapter. Okay.